Hello everyone. Now we will see the stepwise solution of end semester examination of summer 2018. Let us begin with the first question. Question 1A for 5 marks. A question is a 5 kVA 200 volt star connected 3-phase salient pole alternator with direct and quadrature axis reactance of 12 ohm and 7 ohm respectively delivers full load current at unity power factor. Calculate the excitation voltage and full load regulation neglecting resistance. So as usual, first we will see the given data. So as per the question, the given is that is apparent power, that is kVA rating is 5, then line voltage is 200 volt, direct axis reactance 12 ohm and quadrature axis reactance 7 ohm, and we have to find out the regulation at unity power factor. So the phase angle is 0 and the sin phi is 0. Now what we have to find here? We have to find the excitation voltage and full load regulation, and the condition is that we have to neglect the armature resistance. So now equations to be used. As usual, phase voltage is given by the ratio of line voltage to √3. Then apparent power Q is equals to √3 times VLIL. Full load current I is equals to rated kVA multiplied by 1000 divided by √3 VL. As per the equation, Q is equals to √3 VL IL. Now tan delta is equals to Ixq cos phi divided by V plus Ixq sin phi. Then to estimate the direct axis current ID, the equation is I multiplied by sine of psi. Psi is what? It is the sum of phase angle phi and delta. So it is sine of phi plus delta. Excitation voltage E naught is V cos delta plus IDXD. As armature resistance is neglected, that's why IQRA is neglected in this excitation voltage equation. And finally the full load regulation. Load regulation is determined by taking the ratio of E naught minus V to the V. Now just put the values here, then we will get the phase voltage, then full load current, tan delta as 89.43, then direct axis current 14.429, excitation voltage is 174.29 volts, and then put the values of calculated E naught and the value of phase voltage, that is voltage per phase 115.47 in equation E naught minus V divided by V. Then we get the full load regulation at unity power factor is 50.93%. Now let us see the next question, question 2A, which is for 5 marks. The question is a 3-phase star connected alternator rated 1600 kVA 13,500 volt delivers output power of 1280 kilowatt. The synchronous impedance of alternator is 1.5 plus J30 ohm per phase. It is in rectangular form. Now we have to calculate here percentage regulation at full load for following power factors, that is unity and 0.8 leading. So first we will see the given data. So as per the question, the kVA rating is 1600. Then line voltage is 13,500 volts. Output power is 1280 kilowatt. Power factor, we have to take the two conditions, that at unity power factor and 0.8 leading power factor. And then synchronous impedance per phase is given as 1.5 plus J30. It is in rectangular form. And what we have to find? We have to find the percentage regulation at unity power factor and 0.8 leading power factor. The equations that we have already seen in the first question, the same equations are used here. but the difference is that open circuit voltage per phase is given by the equation, that is E naught is equals to root of Vp cos phi plus IRe whole square plus Vp sin phi Ixs whole square. So it is the synchronous impedance method to determine the regulation of an alternator. Now using the above equations and taking the condition of 0.8 leading power factor, we can determine the cos phi, right? Because cos phi is equals to what is the ratio of kilowatt to kVA. So using that we can find out the load in kVA. Load in kilowatt is given, that is 1280, so divided by 0.8, so we get the load in kVA, that is 1600 kVA. Then put that kVA in full load current, I is equals to, so that we can calculate the full load current, that is 68.42 ampere. Then put that values in equation. E naught is equals to root of Vp cos phi plus IRe whole square plus Vp sin phi plus Ixs whole square. Then we get the voltage per phase at 6860 volts, right? So put that E naught and Vp in the percentage regulation equation, that is E naught minus Vp by Vp into 100. Then the regulation is minus 11.98 percentage, as it is a leading power factor, that's why the regulation is in minus. Now the second condition is we have to determine the regulation for unity power factor. So using the same equations, so for unity power factor we can calculate the load in kVA by taking the ratio of load in kilowatt to the cos phi. So 1280 divided by 1 is equals to the 1280 kVA. Then phase voltage will remain same, that is 13,500 divided by root 37794 volts. Then to determine the full load current, take the calculated load in kVA multiplied by 1000 and divided by root 3 VL. Then we get the full load current as 54.74 amperes. Then put the cos phi as 1 and sin phi as 0 and calculate the open circuit voltage per phase. So that is 12,291 volts. So put that values, then percentage regulation at unity power factor is 57.69 percentage. Next question is question 2a, which is also for 6 marks. The question is an 11 kilovolt 3-phase star connected synchronous generator delivers 4000 kVA at unity power factor when running on constant voltage, constant frequency bus bars. If the excitation is raised by 20%, determine kVA and power factor at which machine now works. The steam supply is constant and the synchronous reactance is 30 ohm per phase. Neglect power losses and assume magnetic circuit to be unsaturated. So here, as per this question, we have to assume the excitation is raised by 20%, and according to that we have to determine the kVA rating and then power factor of the machine at new kVA, right? Okay. So first write down the given data. So as per the question, the applied voltage is that is line voltage is 11,000 volts. Then kVA rating is 4000 kVA when before the excitation is raised by 20%, and that is for unity power factor. Then synchronous reactance 30 ohm per phase. What we have to determine here? We have to determine the kVA when the excitation is raised by 20% and the power factor. Now continue to this. Equations to be used. So the voltage per phase, as we have already seen, it is equals to VL by root 3. Then reactance drop, product of current and synchronous reactance, then generated EMF per phase is equals to square root of the phase voltage plus the drop, that is the product of IS and the square of that. Then the KVA rating is given by the product of RMS values of voltage and current. Therefore, phase voltage is calculated by putting the value of line voltage, that is 11,000 volt. So the answer is 6350 volt, the phase voltage. Then KVA rating. KVA rating is given of 4000 kVA. Then put the value of calculated phase voltage here. Then as per the equation of kV is equals to VI, we can calculate the current, and that is the current due to the resistance, that is IR, is equals to 630 ampere. Then reactance drop, take the product of current and synchronous reactance per phase. The current is 630, reactance is 30. Then the generated EMF per phase, put the value of phase voltage and the drop, that is IXS. So the answer is generated EMF per phase is 19938. First we will draw the phasor diagram with the values before the excitation, that is with V as a reference, and then with the values after the excitation, that is IXS drop. So before the excitation, take V as a reference, so draw it parallel to the horizontal axis, then show the vector I lagging behind this V by an angle phi, then show the in phase component IR in phase with the voltage V, right? Then show the vector for the drop IRXS at 90 degree to the applied voltage V. Then the induced EMF is equals to what? It is the vector sum of V and IRXS drop. So E is equals to the square root of V square plus IRXS whole square, that we already calculated. Then if the excitation is raised by 20%, then the active component of current, that is I cos phi, and that is indicated by IR here, it will remain same, but the reactive component of current, and due to that the drop IXS drop will be different, and due to that the induced EMF will be different, right? So here the E dash, if the excitation is raised by 20%, is equals to the square root of V plus IXXS whole square plus IRXS whole square. We'll see that on next slide. So here, if the excitation is raised by 20%, then the generated EMF per phase is equals to 1.2 multiplied by the induced EMF before the excitation, and that excitation is that induced EMF is 19938. So now the excitation is raised by 20%, so multiplied by 1.2. Right, so we will get the generated EMF per phase. Then as per the phasor diagram, E dash square is equals to V plus IXXS whole square plus IRXS whole square. So using this equation we can determine the value of reactive component of the current, that is IX, right? Then using this IX we can find out the new value of armature current, and that is what? Square root of in phase component of the current, the square of that, plus the square of reactive component of the current. So I is equals to the square root of 630 square plus 7738.611 square, right? Now here 630 is the in phase or active component of the current, and 7738.611 is the reactive component of the current, and that is Ix. Right, so using the IR and Ix, here the new value of armature current is determined. Then using that we can find out the power factor, because we know that in phase component of current is equals to I cos phi. So IR is equals to I cos phi we can take here. So IR is what? 630 ampere. That is calculated value, and that's why the power factor can be calculated as IR by I, right? So IR is what? 630 ampere, and I is 7764.212 ampere. So take the ratio of this, then we will get the power factor, and that is 0.08. And this is the inductive circuit, so we can say that the power factor is the lagging power factor. Now finally we can determine the new value of kVA. So take the product of voltage and new value of armature current, right? So finally we'll get the kVA, but that is in MVA. So that is the answer. Now the next question is question 3b, which is also for 6 marks. The question is, a 3-phase 10 kilowatt synchronous motor is connected to 1000 volt supply and has synchronous reactance of 10 ohm per phase. Find the value of minimum current and the corresponding induced EMF for full load condition. The efficiency of the motor is 80%. Neglect armature resistance. First, as usual, we'll see the given data. So here the motor output is given, that is 10 kilowatt. Then supply line voltage is 1000 volt. Then synchronous impedance as armature resistance is neglected, and that is equals to the synchronous reactance per phase, and that is 10 ohm. Then efficiency of the motor is given, that is 80%. Now what we have to find? We have to find out the minimum current, then EMF. Now we'll see the equations to be used. First, efficiency, we know that efficiency is motor output power divided by motor input power. Then motor input power is equals to, for 3-phase system with the line values, is √3 VLIL cos phi. Then impedance drop, we have already seen it, right, in the previous question. That is the product of I, Z. Here the armature resistance is negligible, that's why the impedance drop is equals to the product of current and synchronous reactance. Then phase voltage, that is voltage per phase, is equals to VL by √3. Then induced EMF per phase, that we already seen, is equals to the vector sum of phase voltage and impedance drop. So EPH is equals to the square root of VPH square plus IZ square. Line induced EMF, as seen earlier for VPH, so it is equals to √3 EPH, because we know that in 3-phase AC circuits line voltage is equals to √3 times the phase voltage. We have the given data and we know the equations to be used, so by putting the values in the equation we can find out the answer, right? So first we will calculate the values and then we will see the phasor diagram. Motor input power is the ratio of motor output power to the efficiency. So put the value of output power and efficiency, then we will get the motor input power. Similarly, to find out the in-phase or active component of the current, take out the I cos phi from the equation √3 VL IL cos phi, and put the value of motor input power here, that is of 12,500 watts, right, and divided by √3 VL. So we will get the I cos phi as 7.216 amperes, and this is the current, and this current is minimum when power factor is unity. So with this unity power factor, we can say that this I is equals to I cos phi. Then using this current, we can find out the impedance drop. So put the value of this minimum value of current and the synchronous reactance per phase. So that is the product of 7.216 and 10. So the impedance drop is 72.16 volts. Now this is the phasor diagram. The phase voltage is calculated by taking the ratio of VL to the root 3, right? So phase voltage is 577.35 volts. So that is taken as a reference. Then show the impedance drop, that is IZ is equal to 72.16 volts at 90 degree to this. Why? Because the armature resistance is neglected here, right? That's why the impedance drop can be shown at 90 degree to the voltage, and then the vector sum is what? EPH, right? Then we can show the current, that is minimum current I in phase with the voltage, that is VPH. Now you see the induced EMF per phase, which is the resultant of phase voltage and impedance drop. So first we'll find out the phase voltage, then induced EMF by taking the vector sum of phase voltage and impedance drop, that is equal to square root of VPH square plus IZ square. Then using that we can find out the line induced EMF, that is root 3 times the phase voltage. So put the value of calculated EPH and get the line induced EMF, and that is the answer. This is the next question, question 3b, which is in all and which is also for 6 marks. The question is, a 3000 volt 3-phase synchronous motor running at 1500 rpm has its excitation kept constant corresponding to no load terminal voltage of 3000 volt. Determine the power input, power factor and torque developed for an armature current of 250 ampere if the synchronous reactance is 5 ohm per phase, right? Then we have to determine what? Power input, power factor and torque developed. And we have to neglect here armature resistance. Now we'll see the given data. So as per the question, the line voltage is 3000 volt. Synchronous speed 1500 rpm. Then synchronous impedance is equal to the synchronous reactance per phase, and that is 5 ohm. And it is why? Because armature resistance is negligible. What we have to find here? We have to determine the power input, power factor and torque developed for an armature current of 250 amperes. Now we'll see the equations to be used. Torque developed, that is equals to the ratio of motor input power minus armature copper loss divided by 2 pi ns divided by 60. So here we are taking the synchronous speed in RPS, that's why divide the synchronous speed by 60. Then motor input power, that is equals to root 3 VL cos phi. Then impedance drop equal to IZ, and that is equals to IXS, because here armature resistance is neglected, that's why the impedance is equals to the synchronous reactance. Then phase voltage, that is equals to VL by root 3. Then power factor, that is cos phi. And then line induced EMF equal to root 3 times the phase EMF. So put the values and get the answer. So the phase voltage is 3000 divided by root 3, then you will get 1732.051 volts. Then get the induced EMF per phase equal to 3000 divided by root 3. Here the induced EMF per phase is calculated by taking the value of line voltage, that is equals to 3000 volt. Why? Because the excitation is kept constant and there is no load on the motor. That's why the induced EMF and the terminal voltage both are same. That's why here again we have taken 3000 volt as the line induced EMF, and that's why the induced EMF per phase is equals to 3000 by root 3, and that is same as the phase voltage. Input line current is equals to the input phase current is equals to 250 amperes, because we know that in star connection the line current and the phase current are same. Then impedance drop, put the value of 250 ampere current and synchronous reactance, that is 5 ohm. We will get the impedance drop, that is 1250 volts. Then internal angle, we can take it as 90 degree. Why? Because the armature resistance is negligible. So according to that we can draw the phasor diagram. Right, so assuming armature current lagging behind the supply voltage band angle phi, so as shown in figure, that is phasor diagram. So take V as a reference, then show the current lagging behind V band angle phi, right? Then show the vector, that is impedance drop ER at 90 degree to the current vector, and then the resultant is E, right? So according to the phasor diagram in triangle AOB, we can get the equation E square is equal to V square plus ER square minus 2 VER cos of 90 degree minus phi. So here put the values and we can get angle phi. Right, so first we'll get the sine phi and then take the sine inverse of that. So the angle phi is equals to 21.15 degree. Then using that we can determine the power factor, that is cos of phi, and that is 0.9326 lagging. So this is the answer. Next, motor input power is equals to root 3 VL IL cos phi. So just put the values. Then we will get the motor input power as 1212 kilowatt. Then torque developed. Now the motor input power is calculated. Armature copper loss is neglected here, right? So just put the input power and synchronous speed and get the torque developed in Newton meter. So that is the answer. The next question is question 3B, which is for 5 marks. The question is a 400 volt 3-phase star connected synchronous motor has armature resistance of 0.2 ohm per phase, synchronous reactance 2 ohm per phase. It takes a current of 25 ampere from supply. Calculate the back EMF induced in the motor if it works at 0.8 power factor leading. The given data is line voltage 400 volts, synchronous reactance per phase is XS is 2 ohm, then armature resistance per phase RA is 0.2 ohm, motor current is 25 ampere and power factor is 0.9 leading. And what we have to find, we have to calculate the back EMF induced in the motor if the motor works at 0.9 power factor leading. Now the equations to be used, that is how to find out the synchronous impedance, that by taking the root of vector sum of Ra and Xs, that is root of Ra square plus Xs square. Then impedance drop, it is the product of current and impedance. Then as usual, voltage per phase is the ratio of line voltage to root 3. Then induced EMF per phase is calculated as E square is equals to V square plus ER square minus 2V ER cos of 90 plus phi, or we can take theta plus phi. If the armature resistance is neglected, then that ER will be at 90 degree to the current, and then that's why we can take the theta as 90 degree. So here it is cos of 90 plus phi. So you see that, and the line induced EMF is root 3 times the phase voltage. Now here assuming armature current leading the supply voltage by an angle phi, so as shown in phasor diagram. So in triangle AOP we have E square is equals to V square plus ER square minus 2V ER cos of theta plus phi. So here theta is the angle in between I and ER, which is less than 90 degree, and phi is the angle in between I and V, that it indicates that current leads the voltage by an angle phi. That's why here we have to take cos of theta plus phi. Why? Because we are taking the triangle AOB. So that triangle is what? So angle of the triangle is cos of theta plus phi. So using that we can find out first the synchronous impedance, that is root of 0.2 square plus 2 square is approximately 2. Then impedance drop IZ, so take the calculated Z, that is 2, and the given 25 ampere current. So the impedance drop is 50 volt, and that is nothing but the ER. Then phase voltage, that is voltage per phase, is 231 volts. Then according to the given power factor of 0.9, we can calculate the phase angle, that is by taking the cos inverse of 0.9, so it is 25.84 degree. Then by taking the ratio of Xs and Ra, and then the tan inverse of that, we can find out the theta, that is theta is equals to tan inverse of Xs by Ra. Xs is 2, Ra is 0.2, so the theta is 84.28, and then angle is theta plus phi, that is 110.12 degree. So according to that, the induced EMF E square is equals to 231 square plus 50 square minus 2 into V is 231 multiplied by ER is 50 and cos of theta plus phi. So the answer is 63807. Now take the root of that, then that induced EMF is 253 volts. Then to calculate that line induced EMF multiplied by root 3, then that is 438 volts. So it is the answer. The next question is question 4a for 6 marks. The power input with the rotor of 440 volt 50 Hz 6 pole 3 phase induction motor is 80 kilowatt. The rotor EMF is observed to make 100 complete alterations per minute. Calculate the slip, the rotor speed, the mechanical power developed, the rotor copper loss per phase, and the rotor resistance per phase if the rotor current is 65 ampere. Now in this question, the rotor EMF is observed to make 100 complete alterations per minute. Means what? There are 100 complete cycles per minute. So according to that, we have to calculate the rotor frequency, that is by taking the ratio of 100 and then 60, because in 1 minute there are 60 seconds, so cycles per second will be the frequency in hertz. Continue to that, the given data is line voltage 440 volts, Number of poles 6, input power is 80 kilowatt, and the rotor completes 100 complete alterations per minute. And we have to find out the sleep, rotor speed, mechanical power developed, rotor copper loss per phase, and the rotor resistance per phase if the rotor current is 65 ampere. Now how to find out the rotor resistance per phase? Because if the copper loss is with us, then by taking the product of I square R and the calculated rotor copper loss, we can find out the rotor resistance per phase. So supply frequency is given, that is 50 Hz. Then rotor EMF frequency F dash is equals to what? 100 alterations per minute divided by 60. That is 100 divided by 60 cycles per second, that is Hertz. So it is 1.667 Hertz. Then slip S is the ratio of rotor frequency to the supply frequency, that is F dash divided by F, and that is 0.03. Now use this calculated slip to find out the rotor speed. So for that, first we will find out the synchronous speed by taking the ratio of 120 F divided by 6. So it is 1000 rpm. Then the rotor speed N is equals to the product of 1 minus S and synchronous speed. So it is 970 rpm. Then using that we can find out the rotor copper loss per phase, and it is per phase, that's why divided by 3. So the rotor copper loss is calculated by taking the S times the rotor input, right? So rotor input is given as 80 kilowatt, so multiplied by S, that is 0.03, and to find out the rotor copper loss per phase, divided by 3. So the rotor copper loss per phase is 0.8 kilowatt. Now the mechanical power developed is calculated by taking the rotor input P2 multiplied by 1 minus S, and it is 77.6 kilowatt. Then the rotor resistance per phase, as I have already explained, that by taking the rotor copper loss as I2 square R2, so we can find out the R2. So R2 is equals to rotor copper loss per phase in watts divided by R2 square. So rotor copper loss per phase is 0.8, so make it in watts, and then 0.8 multiplied by 1000 divided by 65 square. 65 current is given, so the rotor resistance per phase is 0.189 ohm. Now let us see the next question. Question 4a, which is for 5 marks. The question is, determine the slip at maximum torque and ratio of maximum to full load torque for a 3-phase star connected 6.6 kV 20 pole 50 Hz induction motor. Its rotor resistance is 0.12 ohm and standstill reactance is 1.12 ohm per phase. The motor runs at 292.5 rpm at full load. So what we have to determine here? Slip at maximum torque and ratio of maximum to full load torque. First we'll see the given data. So as per the question, the line voltage is 6.6 kV, number of poles 20, then rotor resistance, that's why R2, it is what? Rotor resistance, okay, that's why it is indicated as R2, and it is 0.12 ohm per phase. Then standstill reactance, that is X2 is equal to 1.12 ohm per phase. Then full load speed is 292.5 rpm, and we have to determine here slip at maximum torque and ratio of maximum to full load torque. So the synchronous speed, we know that what is the equation? Ns is equals to 120 F by P. So put the value of F and P. and synchronous speed is what? Then 300 rpm. Then full load slip is calculated by the ratio of ns minus nf to ns. What is ns? Ns is the synchronous speed, so put it as 300 rpm. Then full load speed is given as 292.5, so take the ratio of that. Then the full load slip is 0.025. Then with this we can find out the slip corresponding to maximum torque. So S max is equals to the ratio of R2 by X2, and that is 0.101107, and that is the answer for slip corresponding to maximum torque. Then we have to find out the ratio of maximum to full load torque. So put the maximum slip and full load slip. Then we can have a ratio of maximum to full load torque, that is 2.256. This is the answer. The next question is question 4a, which is in OR, and it is also for 6 marks. The question is, the rotor resistance and reactance per phase of a 415 volt 4 pole 50 Hz 3-phase induction motor is 0.024 ohm and 0.12 ohm respectively. Find the speed at maximum torque. Also find maximum torque in Newton meter. Consider ratio of stator turns to rotor turns as 1. So first see the given data. Voltage is 415 volts, number of poles 4, rotor resistance 0.024 ohm per phase, as it is a 3-phase induction motor, and we know that in 3-phase induction motor there are two constructional parts, rotor and stator. So the rotor parameters are indicated by the suffix 2. That's why R2 here indicates rotor resistance and X2 indicates rotor reactance, and both are per phase value because this is a 3-phase induction motor. Then what we have to determine here, speed at maximum torque and maximum torque. First find out the synchronous speed by using the equation 120 F by P. So put the value of frequency and number of poles. So we'll get the synchronous speed as 1500 rpm. Then slip corresponding to maximum torque by taking the ratio of R2 and X2, and it is 0.2. Then speed at maximum torque, so put the value of slip corresponding to maximum torque in the equation, ns in bracket 1 minus s. So in place of s, put here s max. So we'll get the speed at maximum torque, and that is 1200 rpm. As in question it is given that the ratio of rotor turns to the stator turns is 1. So using that we can calculate the rotor induced EMF equal to KE1. So that's why it is equals to 1 multiplied by 415 by root 3. Stator EMF is given, that is 415, and it is the line voltage. So get converted into phase voltage, and that is 415 by root 3. Turns ratio is 1. That's why the rotor induced EMF per phase is 240 volts. Then by using the equation K dash E2 square divided by twice X2, we can find out the maximum torque. So put the value of K dash as 3 by 2 pi ns divided by 60, and then E2 and X2, we will get the maximum torque, and that is 4560 Newton meter, and this is the answer. Now the next question is question 5, which is for 10 marks, and that is of circle diagram. So the question is a 5 kilowatt 400 volts 4 pole 50 hertz delta connected motor gave the following results, and it is assumed that the stator resistance is 1.6 ohm per phase. Now the data by no load test is voltage 400 volts, current 3.1 and power is 350 watts. The data by block rotor test, it is voltage is 52 volts, current 7.6 ampere and power is 440 watts. What we have to do here, we have to draw a circle diagram to the scale and we have to determine the full load efficiency. So let us see the given data first. So as per the no load test, no load voltage is 400 volts, no load current is 3.1 ampere and no load power is 350 watts. So using that we can find out the no load power factor, and that is equals to P0 by root 3 V0 I0. So no load power is given, that is 350, then no load voltage is 400 and no load current is 3.1. So put that values, so we'll get the power factor, that is no load power factor as 0.163. Then using that find out the no load phase angle. So take the cos inverse of 0.163. So the no load phase angle is 80.62 degree. Now short circuit current with normal voltage applied across the stator can be calculated as ISC is equals to the short circuit current 7.6 multiplied by no load voltage to the short circuit voltage, that is 400 by 52, and that is the current, that is short circuit current with normal voltage, and it is 58.46 amperes, right? So using that we can find out the short circuit input with normal voltage, that is PSC, and that is equals to 58.46 divided by 7.6 whole square multiplied by 440. Right, what is here 58.46? It is the short circuit current with normal voltage, and what is 7.6? It is the current that we take it from the short circuit test readings, right? Then short circuit power factor cos phi SC is equals to PSC by root 3 V0 ISC. So just put the values and give the short circuit power factor as 0.64. Then short circuit phase angle, take the cos inverse of 0.64. Then we get the short circuit phase angle as 50.20 degree. Here the values are not as per the given data, so that may be due to some inaccurate values in questions. Now short circuit current with normal voltage applied across the stator. Okay, that we have seen. So now we have to decide the current scale, and that is 1 centimeter is equals to 5 ampere. So here we are taking 1 centimeter is equals to 5 ampere. By using the results obtained from no load and block rotor test on 3-phase induction motor, we have calculated the no load phase angle phi naught and short circuit phase angle phi SC, which are used here to draw the circle diagram. So with O as origin, take OV along the y-axis, then with O as origin, draw OO dash, that is equal to no load current at an angle phi naught to V, that is it is lagging behind V by an angle phi naught. Then with O as origin, draw OA, that is equals to the short circuit current with normal voltage, and that is to be drawn at an angle phi SC to V. Then draw OF perpendicular to OD. Then from O dash, draw a line O dash G parallel to OF. Then to get the center of the required circle, draw a perpendicular to the line O dash A. First join the line O dash A and then take a perpendicular to line O dash A that will bisect the line at point B, and then it will intersect the line O dash G at C. So with C as the center and O dash C as the radius, we can draw the semicircle, and that is shown on the next slide. So here with C as the center and O dash C as the radius, we have drawn a semicircle. Then at an angle phi 1, draw or join OH. So to get the point H, draw a line parallel to O dash A, that is output line, that also represents the rotor current referred to the primary side, that is I1 dash, right? So OH will indicate the current I1, and that is at an angle phi 1 to V. Then to estimate the maximum output power, maximum torque and maximum input power, draw the intercepts to the circle diagram. So here first draw the points O dash D. So O dash D line indicates the torque line. Then the O dash A is already joined, and the O dash A indicates the output line, right? So to get the maximum output power, drop perpendicular from point H, and then that will cut the lines O dash A, O dash D and O dash C at the points K, L, M, right? So the HK, it is the vertical intercept HK indicates the maximum output power. Now to estimate the maximum torque, draw a line parallel to the torque line, then that will in, intersect the semicircle at O dash, that is it will be tangent to the semicircle, and then O dash O will indicate the maximum torque, right? Then to get the maximum input power, drop a perpendicular from point A, and means what? How to get the point A? Draw a line parallel to the O dash G or OF, then that will be tangent to the semicircle, right? That will cut the semicircle at point A. Then the vertical intercept AF will indicate the maximum input power, right? Also it will indicate the total losses. EF indicates the no load losses, that is fixed losses. Then AD rotor copper loss, and DE stator copper loss, right? So the points HK, then HL, HM and HN. So these are the energy components of the line current I1, and that will see how these are used to calculate the sleep, power factor and efficiency at full load. So to determine power scale, a perpendicular AF through A is drawn, that we have already seen. So AF represents the total input on short circuit with normal voltage, which is 26034.132 watts. Since AF is equals to 7.15 centimeter, we can measure it by scale, and it is 7.15 centimeter. So the power scale is what then? 26034.132 divided by 7.15, and that is 3641.137 watts per centimeter. So At full load, we can calculate the power factor by taking the ratio of NH, that is the energy component of the current I1, divided by OH. OH is what? That is the line current I1 at an angle phi 1, right? So by taking the ratio of that, we get the power factor as 0.9. Then output can be calculated by kH and multiplied by power scale. So kH, measure it in centimeter by scale, so it is 2.15 centimeter, and multiplied by power scale, then we will get the output in watts. Then find out the efficiency by taking the ratio of kH to NH and multiplied by 100. So we will get the efficiency, and the ratio of that kH by NH is 2.15 divided by 4.61 is 0.466, multiplied by 100, then we will get the efficiency, that is 46.6%, and that is the answer. So I think all the questions are clear to you, and if you are having any doubts, any confusion, then you can contact me, you can call me, right? Thank you.